So, Gallian's group theory exercises once again. Now, these next two, that is 55 and 56, are similar to exercise 54, which we already solved in the previous video. So, what I am going to do, I won't solve these two and I will leave the solutions to you, because you can see that they are exactly similar. Here also we are starting with some positive integer n. In this case, n is given to be an odd positive integer. Then an, the alternating group of degree n, has an element whose order is strictly greater than 2n if and only if n is at least 13. So based on the solution that we have seen of exercise 54, we know actually how to proceed. We have to first consider the odd values of n less than 13, and in each case, for each such value, we have to consider the corresponding alternating group. And there, looking at the cycle structures of the elements, we have to guess what the possible orders are, and we will see that we will never encounter in any of such cases, I mean for the odd n's less than 13, we will never encounter a case where we will have an order that is greater than 2n for that particular value of n, proving that those cases can be ruled out. But then you consider n to be greater than or equal to 13. It may be the case that you have to consider n equal to 13 separately. I don't know, it will, I mean whatever turns out to be the case, you have to write the solution accordingly. And in those cases, you have to in fact show that there is an element in the corresponding an whose order is strictly greater than 2n. And if you find it difficult to really see how such an element can be produced, or if you fail to figure out what such an element can be or how its cycle structure should be, then you can just always look at the answer that is available at the end of the text, because this is an odd numbered exercise, so the answer is already there. And just like that, you have this next one, where instead of an odd n, now you have an even n. And in this case, again, an has an element of order greater than 2n if and only if this time n is at least 14. Okay, so these two I am leaving to you. So let us now see this next one, exercise 57. Now in this one, we are viewing the members of D4, the dihedral group D4, which of course, as we already know, is the group of symmetries of a square, as a group of permutations of a square whose vertices are labeled like this, consecutive vertices 1, 2, 3 and 4, and in fact it's already there described in example 3. Now if we interpret the elements in D4 as permutations of these vertices, because you can do that, right? For example, let us just draw a square and see what this thing means. If you think of the elements of D4 as permutations of the vertices, then you have to figure out which geometric symmetries correspond to the even permutations. That is, which one of these are even elements in the corresponding symmetry group. So if we draw a square, say like this, it won't be a perfect, so we just have to see what the thing means. say this is your square. And you can of course name the vertices like this in whatever manner you want. Now you change this by performing some geometric transformation on the square. I mean the kind of transformation that again brings the square in it so that it looks just like before, and that's why it's a symmetry of the square. Say you do this 1 4 3 2 or like this. Okay, so what we did here, what is the geometric transformation that we applied on this to get this? Namely, the one which brings 1 in place of 4. I mean 1 now comes here, 4 comes here, 3 goes there, and 2 takes the place of 1. That means this is R90, rotating the square about its central point through an angle, by an angle 90 degree in the counterclockwise direction, in the counterclockwise sense. And the central point of course is the point you already know, is the point of intersection of the two diagonals. Now instead of thinking of this thing as a geometric transformation, you can also think of it as a permutation of the vertices. Because if you think of it, say you define a mapping like this, say you name it phi, and you have the original vertices like this. Now 1 takes the place of 4. You can think of it in that way also, or you can also what is more natural, I mean what I am trying to, yeah, you can think of it like this also. 1 becomes 2, then 2 becomes 3, 3 becomes 4, and 4 becomes 1. So you get the permutation. This way you can interpret the other elements of D4 also, each one of them as a permutation. You will see that the corresponding permutations form a group which is in fact the same as the group D4 in the sense of being isomorphic, although we have not really got the notion of isomorphism yet, but still I am saying as groups they are the same thing. So as permutations we can of course ask whether it is even or odd. So that thing they are asking in the exercise. This one however is it does not really make sense to ask whether the geometric transformation R90 is even or odd. That does not make sense, but when you interpret this as a or rather more rigorously speaking, when you associate this R90 with a permutation, then you can of course ask whether it's even or odd. So that is the interpretation, and based on this you have to figure out which geometric transformations correspond to odd permutations, and it turns out that the ones that do are these. This is of course your identity transformation, which does not actually do anything to the square. Then you have R180, which is rotating the square in the counterclockwise sense through an angle 180 degrees. And then you have these two flips, of course, H and V. H is flipping the square along a horizontal line which cuts the square into two equal halves. That is, you have this square, you have this line, you flip the square along this line, and there is a vertical flip also, where this is your axis about which you are flipping. So it turns out that these transformations correspond to even permutations, and the other transformations that you have in this group D4 correspond to odd permutations. But you note one thing, that this solution is just simply, if you just simply write like this, that is not enough. You have to really say what the corresponding permutations are, and that is why exactly how they are even. Okay, so that you have to show, and you have to also nicely write the complete solution. So this is more like a hint, but the writing part I am leaving to you, and I am leaving many things to you because by now you have seen many of the solutions. So it would be nice, it would be a nice exercise for you to start writing the things on your own. And then this next one, note one more thing, that merely saying that these are the transformations that correspond to even permutations is not enough, because this does not say why there is not more than these four. You have to also show, because of that the other transformations that you have, the other elements in B4 correspond to odd permutations, so that these are the only ones corresponding to even permutations, and that will give you a complete solution. Next exercise 58, viewing. It's also similar to this one, but it's not about a square but rather a regular pentagon. Viewing the members of D5, as a group of permutations of a regular pentagon. With consecutive vertices labeled as 1, 2, 3, 4 and 5. What geometric symmetry corresponds to the permutation one, 4, 2, 5, 3. So here we turn the problem around. There in the previous one we were being asked to say something or figure out what the geometric symmetries are that correspond to even permutations. Here, however, permutation is given and we have to find the corresponding symmetry. Note one thing, that these solutions that you are getting in these videos, after all, they are, all of them are, after all, just some hints. And I am keeping things this way because I do not want to either write or claim that, okay, this is a very nice solution and you should follow it. I'm not doing it that way because I'm keeping things somewhat more open so that you can get sort of hints from these things and then you can write your own solutions. There is always, keep in mind, there is always room for improvement. Unless, of course, some solutions have been seen many times by many people and people already did some improved somewhat. Every time someone went through a known solution, they improved it somehow. Then finally it will reach a final stage. But the things that we usually write, there is almost always, you won't believe if I'm just simply saying, always a room for improvement. If you just leave the solution for a moment, you have got a solution and then you leave it for a moment, for the moment, you come back after say a few hours or maybe a few days, you will see that somehow you can improve it further and then even a little more. Like that, eventually the solution will gain a state where you will, when you see it, you will know it that, okay, now we don't need any more. Okay, so you should not take any of these things as something final. In fact, I am deliberately keeping many things open and unfinished so that you can work on these things. Plus, we have to progress also. There are so many exercises in this book, it's a good thing, but we are attempting each one of them, so it is taking time. But still, we are somewhat progressing at a very slow rate, but still we are progressing. But now if I try to write extremely detailed solution for each one of them, then we won't be progressing. I mean, in any sense, I feel like that. Plus, you will just simply develop the habit of getting everything done for you and you just take it down and forget. Now, you also have to struggle even a little bit. Okay, and there is another one. Which symmetry corresponds to the permutation? Which is the product of these two cycles or transpositions. And this you can understand because we have been asked to find geometric symmetries, so we actually have to draw figures here. Ideally we should draw regular pentagons, but of course I cannot do it here, or more like I will not do it. Here also, let me just keep it in the form of a hint. Than an actual solution. You just have to see what it turns out to be, that's all. Okay, so the vertices, consecutive vertices are labeled as usual. If you want, you can follow the the numbers in the counterclockwise sense also, but I am just choosing to write them clockwise. Okay, and this transforms into this. Oh, see, okay. I have already made a mistake. Do you see what that mistake is? These little circles that I have drawn, they will not be present here because it's not graph theory. These are geometric figures. Sorry about that. Always when I draw this kind of things, I subconsciously I am thinking of graphs. So that's why, but this is the geometric figure. There is no extra point like that which is a circle. You already know these things. Okay, now 1 becomes 4. 4 becomes 2. Okay, 2 becomes 5. 2 becomes 5. 5 becomes 3. 5 has become 3. And 3 becomes 1. So this is our transformation. What transformation is it? You can see that this is the transformation which has taken this one to this position. Similarly, it has taken this 2 to this position, right? Now, if you think of the center of this pentagon, it is a regular, the way I have drawn it, it's not a regular pentagon, but you have to understand that it represents a regular pentagon. Now, it also has a center, and if you join the vertices, to draw the center, I again first considered a circle. No, but there won't be any circle. We get, the more we deal with one part of mathematics, the more we program our brains accordingly, so that even if we don't want to do something, we end up doing it. It's annoying, but it takes time to get rid of a habit. Anyway, so we can join the vertices like this. Now, because our pentagon is regular, all these angles are equal. Each individual angle, they all have the same measure, and that measure is 72 degrees. And to find this value, you just have to simply divide a complete revolution, that is 360 degrees, by 5. That is because all the angles are equal, you get 72 degrees. So that means what we are doing here in order to bring this one here is that we are rotating the entire pentagon in the clockwise sense through an angle 2 times 72 degrees, that is 144 degrees. So this permutation corresponds to a clockwise rotation of the pentagon by an angle 144 degrees. So you have to accordingly write, and if you want you can just simply write it in words, but it's better to draw the figure also, so that we can see clearly why that is the case. And what about that one? Writing a solution or studying something, not just in mathematics but in many other subjects, it is not something final. It's not like you have studied, you have fully understood what you have studied, and you have also solved the problems, and that's just it. The story ends there. It's not like that. It's more like a limiting concept. I mean, the more you come back to it, you will see there is something that was left in the previous viewing. It's disturbing. I mean, it seems like we never reach finality, but we keep on improving. Okay, so again we have to draw 2 more pentagons. Why not? Again. This is not regular, but just something that we can manage with. In order to draw a regular one, we have to carefully keep the angles same. Again, 1, 2, 3, 4, 5. To see what this one will do to the pentagon, here you note one thing, that 1 does not appear here. So that means this transformation will not do anything to 1, it will keep 1 fixed. But it interchanges 2 and 5, that means it changes swaps the positions of 2 and 5. So 2 now gets the place of 5 and 5 gets the place of 2. Similarly, 3 and 4 are swapped. 4, 3. So you can imagine what went on here. There is a perpendicular that you can draw from the vertex 1 to the opposite side 3, 4. Now what happened here is that the pentagon got flipped along this axis, so that 2 and 5 got interchanged and 3 and 4 got interchanged. So that is the physical, I mean the geometric symmetry that this transformation or this permutation corresponds to. So you have to just write it in words that it is flipping the pentagon about the axis of symmetry that passes through the vertex 1. So you can write the geometric symmetry or transformation in words like that. For example, here you write rotating the pentagon. This corresponds the previous one, the previous we don't have it here, but the other one, that 5 cycle, corresponds to the geometric transformation of rotating the pentagon about its center in the clockwise sense by an angle 144 degrees. So that will give you the solution. And I will end things here itself. I know it's a very short video, but we will see other solutions. For some reason I don't have more time tonight. I have to do something else, for which I am sorry, but we will see other solutions in the next Gallian update. And tomorrow, as usual, of course, we will do analysis, where we are going to last Monday what did we do? I think we stated the root test for absolute convergence of a theory. So tomorrow we are going to prove it, and if time permits, we will see the ratio test also. So that being said, I am ending things here. If you want to say something, you can write in the comment section below, or you can mail me at my address. The link will be there in the description. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.